Hello everyone, welcome back to the series. In the last lecture, I introduced the concept of sequential labeling, which will assign a label to each word or token in the given sequence of words. And we started our discussion with the parts of speech tagging and seen how to use NLTK and spatial libraries to assign POS tagging to a token of text. In this video, I'm going to talk on another task of sequential labeling, which is labeling the named entities from the given text. This is called named entity recognition (NER) system. Given a sentence, Sundar Pichai, the CEO of Google Inc., is walking in the streets of California. If I ask you to identify the different entities existing in this sentence, you could say Sundar Pichai is a person, Google Inc. is an organization, and California is a location, right? So this is called named entity recognition. So a named entity recognition system would extract and classify the entities which are different kind of things in the sentence. Let's see what are the named entities. Named entities can be anything from a place, an organization to a person name, and they can even be the time and the dates as well. Identifying these named entities itself is very important because named entities such as who, what, where, when, and so on are often what most people are interested in. So these are very important to be identified. Let's see, for example, you wanted to tag a sentence United States of America as the name of the country. This entire seems to be four words, but it is a single entity that is called the country, geographical location, country. So if you wanted to tag this word like United States of America, how could you will tag like this is the beginning of United is the beginning of the country, states are inside the country, and America is end of the country. So with the boundaries of beginning and ending of the country span, these two are the beginning and ending of the country, and the remaining whatever is inside the boundaries will be inside the country. So instead of labeling this entire United States of America as a single country entity, we can label it as individual with the positional taggings. You can say another example, that is United Kingdom. It's also a single country. So this can be labeled as beginning of the country, B country, and labeled as E country. This type of entity recognition is called customized name entity recognition, called custom NER. Unlike POS tagging, where each word is assigned a POS tag, name entities can span over more than one word. So a span, what is span? A span in NLP is simply a range over one or more contiguous words. These spans can be represented by a combination of the positional tag and a category tag. So there are actually three types of positional tags are there. One is the beginning, which is assigned to the first and the only token of the span. This is the B tagging. And another is assigned inside. Another positional tag is inside. Inside is assigned to all but the first token of the span. And the last is outside, which is assigned to all words outside of any span. In such a way, which is a combination of positional tag and the category tag together, we can assign the tags across which spans across the multiple words. This representation is called IBO or BOI representation of NER tagging. See an example. Let's have a look at this example. If you look at this example, Apple is the first and the only token of organization. So it's been assigned BORG tag. Similarly, if you look at UK, the token UK is the first and the only token of geopolitical entity. So it's been assigned beginning of GPA tag. Now looking at the two tokens, $1 and billion, these two are the monetary expressions. So now this is the first and this is the second monetary expression token. So this been assigned B money and this is been assigned I money inside. This is the beginning of the monetary tag, monetary span. So it's been assigned the label B money. This is the next comes in the next one, I money inside. This is how the BOI or IBOI tagging, which spans across the words, can be done. So the rest of the words, if you look at all the remaining, all the tokens being assigned the tag O. This is the outside of the span, which indicates that this a token belongs to no entity or the no chunk. So let's look at a typical example of NER. Dhaval loves apple, it keeps him healthy. In this sentence, Dhaval is a person and apple is a fruit. Fine? Okay. Now let's look at another sentence. Dhaval loves apple, the company produces the best electronics. In this case, this apple is, Dhaval is a person, common. In this case, this apple is an organization or a company, right? So now the question is this apple fruit or company? How the machine will identify the same word apple differently in these two sentences? That's the question. Look at the simple recurrent neural network which spans across time steps in single direction. In this case, the word apple will have the influence of only the previous two words Dhaval and loves. When we get the sentence, we feed every word one by one to this network. And then it is a kind of looping effect. Correct? At the time T1, I'm feeding the word Dhaval, getting the activation A1. And at the time T2, I'm feeding the word loves and getting the activation A2. Actually, when I'm feeding the word loves to the same network at the same layer where Dhaval can be seen. Already Dhaval has been seen from the activation A1. It's actually a rolled recurrent neural network. If spans across the times, we can see the network like this. So what I'm doing, I'm just removing these all neurons for the cells, whether it is the RNN cell or LSTM cell or GRU cell. So in the single direction recurrent neural network, the output for the word apple is influenced by all the words and the activations before this, which I can show in a different color orange. So for the word, the output for the word apple, which is being influenced by the previous all the words and the corresponding activation functions which I am notating with a different color orange. But for the final outcome of apple, we decided we need of, in order to decide whether this apple is a fruit or company, we look at the future words also, which comes in future. The words that are coming after apple, nothing but in future also we need to consider. That's what we decided. So you need to make changes to this neural network. One way is to add another layer from the right to left. See this? This is the original network RNN spans across the time in one word direction that we have seen in the previous slide. Now the change that we brought into this neural network is we added another layer from right to left. If you look at the activation functions and the arrow scale, so these activations are processing from right to left. Another layer, like a layer. It's the same kind of recurrent neural network cells, only the difference is the activation is going from right to left. So now what happens when I decide whether this apple is a fruit or company? The output y3 hat is a function of A1 and A2. So basically you have the influence of both the previous words Dhaval and loves on your y3 hat. But If you look at these blue lines, because of these lines, you have the influence of your future votes as well. It keeps him healthy. So, with this additional layer of recurrent neural layer, which is coming from right to left, apart from calculating this y3 hat for finding the apple outcome of the apple, not only considering the previous votes from this layered network Dhaval and Loves by the activation functions A1 and A2, it is also considering the activation functions which achieve from the future votes, the votes which comes after the word apple also. This you can see from the all these activations, processor activations coming in the sequence order, which can merge at A3 in order to get, which is going to the final outcome of Y3 hat. All this is called bidirectional recurrent neural networks. Whether it is RNN or LSTM or GRA, whatever the cell is, recurrent cell is, this is called bidirectional recurrent networks. Here are some real world examples of named entity recognition systems that we can see. So I mentioned their ability to scan that is the first is search engine efficiency is one of the applications of named entity recognition. The ability to scan the documents for certain things quickly. Just imagine how NERs can optimize their search engine efficiency. In this case, the NER model scans millions of websites once and stores the entities it is defined in the process. Then the tags from your search queries are simply matched against the website tags. The same concept extends to making recommendations as well, where the tags might instead be extracted from your history to compare it to similar user histories in order to recommend things you might want to check out. And NER helps in reducing the response time by categorizing the user requests also. User requests, the complaints, and the questions filtered by the specific keywords. This works by matching customers to an appropriate customer service agent. This works is similar to a phone free where you would be prompted to provide some information about your request. If you are using an app to communicate with your car insurance company, you might provide some spoken or typed information such as I need to add another vehicle to my car or my car was destroyed by something because of this reason. So you will then be matched to the appropriate agent accordingly. Another interesting use case is automatic trading. For example, you could imagine building a web scraper to get a news articles of the names of certain CEOs, stocks, or cryptocurrencies, then feeding those articles into sentiments classification systems and making your tradings accordingly. So these are all the applications of named entity recognition system. In the next video, I'm going to show you how to use this NER system and with a practical exercise.